Thanks. So it's a pleasure to be here in this Indian Statistical Community meeting. Today I'm going to talk about some recent work that we've done on characterizing stresses in amorphous systems and as well as crystalline systems and the correlations between the stress tensor in such systems. It's work done with a graduate student at TIFR Hyderabad, Roshan Maharana, former graduate student Debankur Das, who is now at University of Göttingen, and Pinaki Chaudhary at IMSC Chennai. So the outline of my talk is I'll present a universal characterization of stress correlations in athermal systems. I'll tell you what I mean by athermal systems in just a bit. We study correlations between the stress tensors, so the local stress fields that develop in such systems, and we look at energy minimized configurations, which is what I mean by athermal. So everything is at a global energy minimum or a local energy minimum, but so it creates force balance configurations at the local scale. Because of that, the stress tensors that develop in such systems have very peculiar properties, which I will discuss. And so what we can do is characterize the stress correlations in these systems across various situations, crystalline as well as fully amorphous packings. And the sort of result that I will show you in today's talk is that at the large length scales, the correlations in the stress tensor are independent of structural correlations and other microscopic properties, and they display universal characteristics. Okay, so when I'm talking about disordered amorphous materials, they're sort of ubiquitous in many different fields of study, including biological physics and foams, for example, in liquid turbulence. You see elasticity emerging in such systems, whereas you can also look at fully amorphous packings of particles which are by themselves elastic, and as a collection they display some random behavior at the short length scales, but at the large length scales they have elasticity emerging. And so how do you model such a wide variety of materials? Well, you create simple computer models, and these can reproduce many characteristics of amorphous materials. And when you look at the stress fields inside such materials, so when you look at a collection of objects, for example, soft spheres, which is a model that has been studied in detail in many different contexts. So what you look at is a disordered arrangement of particles. Each of these particles has some forces between them and some finite size, and you can create, for example, you look at the force on every grain, and you can ask whether every system is in force balance. And so the microscopic forces that appear in such systems have to be balanced at the local level. Similarly for the torque, so you can create, in this disordered material, you can create a stress field, you can create a torque field, but in order for this system to be static, for it to be stable, it has to satisfy the conditions of mechanical equilibrium. So when you want to now try to describe such a system at the coarse grain level, you can create a particle force moment tensor, which is basically you take the packing and you look at all the forces and you look at the distances between the particles, and you create a stress tensor or a force moment tensor, which is not readily amenable to continuum treatments because of the disorder in the arrangement of particles. But you can still try to create theories for the coarse-grained stress tensors, which is something that we did with Shubro and collaborators. Shubro will discuss this in detail, I'm sure. So you can sort of postulate in this random arrangement of particles a partition function where D is basically like the stress tensor. I won't go into the details here. And if you postulate a Gaussian action for the stress tensor, you can compute the correlations in in Fourier space, which look a little complicated, but what is important here is this lambda matrix is basically the mixing tensor between the different components of the stress tensor. And for an isotropic mixing matrix, you can derive the correlation functions in Fourier space for this collection of packings, assuming this sort of Gaussian action. And these display pinch point singularities. I won't go into the details there, but you can actually sort of do this in 2 dimensions, and you'll see that in Fourier space, so this is the correlation functions between the XX components of the stress tensor. So this sigma xx correlation function in Fourier space has this very nice sine to the 4 theta dependence, and you can actually do this in 2 dimensions, and you can derive these very nice results, assuming elasticity matrix or a mixing matrix which resembles the elasticity matrix in 2 dimensions. So I won't go into much more details of this, but we can now try to do the same calculation from a microscopic model. So there are some microscopic models that we can actually do some analytic calculations on. For example, you can create a triangular lattice of springs, and you can put some disorder in the spring network. You can create packings of soft particles which have overlap between them and some energy of the overlap. Or you can also look at some long-range models where the interaction between this particle in the center extends all the way to the third or fourth shell. And so in a short-range model, this is sort of a paradigmatic harmonic interaction between particles. You can introduce quench disorder into the radii of the particles. And if you do such a thing, what you can do is you can start with a triangular lattice arrangement, and as you vary the sizes of the particles, you can create all the way from crystal all the way to an amorphous packing. So eta is the, if I just go back, eta is the quantification of the amount of disorder in the radii of the particles. So you start with a triangular lattice arrangement, and you increase or decrease the size of some of the particles. So the sigma ij here represents the quenched interaction radii between the particles. And if you increase the size of the particles, you can actually start from a triangular lattice and go all the way to an amorphous packing. And you can then also do the same thing with a slightly longer range model, where you can create quench disorder between the sizes of the particles, and this delta, which is basically a tunable parameter, allows you to tune between a crystal and an amorphous packing. And so this is sort of another paradigmatic model, which is Lennard-Jones with a cutoff that is used in systems which display glassy dynamics and so on. So using these microscopic models, we can now sort of create a crystalline arrangement of particles in a commensurate box, or we can look at it in an incommensurate box, or we can change the ratio of the box sizes and so on. And when you have very little disorder, eta is the disorder parameter, you basically get a polycrystalline system. But as you keep increasing the amount of disorder, you can create all the way from a crystal all the way to an amorphous packing. And you can measure now the stress tensor, or you can also theoretically predict the correlations between the stress tensor, because you have a small amount of disorder in the system. And here are our theoretical predictions for near-crystalline packings. So this is in Fourier space, so this is kx and ky. This is the correlations between the components of the stress tensor for a wide variety of different disorder. Eta is the disorder strength. And you can see that the microscopic theory actually predicts very well what you see in the actual system, and measured from numerical simulation. So this is, for example, the correlation between the XX components of the stress tensor. Similarly, for the XY components of the stress tensor in Fourier space, you can predict this. But then you might ask, where is the signature of the crystalline packing emerging? Well, so in near-crystalline packings, okay. So in near-crystalline packings, you can actually show. So this is the full correlation in Fourier space. You can show that near the edges of the Brillouin zone, you have some non-crystalline behavior emerging, but at close to the k equal to 0 point, which is basically the large length scale behavior, we see the same predictions that emerge from the Gaussian action that I told you about at the beginning. So this is just another illustration of the same point. In the crystal, which is the near crystalline packing, where you have stress fluctuations, but on a crystalline background, you see this kind of correlation function. And if you zoom in here, you see this pinch point singularity developing in Fourier space. Similarly, for the amorphous case, you see the same structure, but only in the k going to 0 limit. So the large length scale correlation functions actually are universal across the crystal and amorphous package. And of course, you can also check it in multiple different contexts. For example, changing the box shape, and also changing many different macroscopic parameters in the system. And we find that the correlation functions look exactly the same, independent of what the background structure is. And so this is sort of the final slide, where we have measured these correlation functions in a wide variety of situations, including in the short range model, including in the long range model, adding a large polydispersity, changing the way that we have created the packings, and we've also sort of measured it in different geometries, and we see that the predictions from the crystalline theory at large length scales matches the predictions that we have from the fluctuating Gaussian action theory, and also matches very well with the numerical simulations that we have. So these lines represent our microscopic theoretical derivation of these correlation functions, and the points represent our numerical simulation. And I won't go into the effect of the pre-stress. So yeah, in summary, we presented a universal characterization of stress correlations in amorphous systems as well as crystalline packings. And the correlations show surprisingly universal characteristics independent of what the local packing structure is at large length scales. They do seem to depend, curiously seem to depend sensitively on how much pressure you have put initially on the packing, but that is a sensitive dependence which really doesn't show up at the largest length scales in a very noticeable manner, but is there. In summary, the simple sort of crystalline lattice arrangement of particles that we created allows us to do a microscopic derivation, which then also allows us to match predictions from field theory that have sort of recently also been discovered. Yeah. So with that, I'd like to thank you and take questions. Yes, please. Yeah. No. So the lattice model. Sorry. Yes.
Simple things that we know. They are a consequence of full packing, these universal features. Yes. What's the analog of that here?
So the analog is that the stress tensor, the divergence of the stress tensor must be zero everywhere. So it is exactly analog of full packing.
Exactly the analog of that.
Exactly. So, so here the rho external, which is the charge,
right,
is zero in this case. So
I see.
Yes.
How does this? In this field theory, of course, you don't introduce strain. You work purely in the language of stresses, right?
Yes.
So how does this compare with Lubinsky and their non-affine elasticity? Because they also compute stress fluctuations. They of course have a strain theory, but they have this disorder introduced in the elastic moduli.
Yes, so that I'm not entirely sure how to map it onto that theory, but that's an interesting question. So there are multiple derivations of correlation functions, which I hope that the microscopic derivation that we have from these models will shed some light on that. But I don't have an immediate answer in that case. Yeah. Yes, Shantanu, please.
So do you consider friction?
No, so these are, for example, the models that we are creating, including these. Once you have a potential of this sort, you cannot include friction. So, but that would be very interesting. So you can actually do simulations and check. So for example, in shear jamming studies, we plan to do that in next, where you can create the forces without sort of invoking a potential of this sort. But these are purely frictionless potentials, these two.
Yes, just one more.
Yes,
this for large value of eta, where you consider the deformation, that like the particle deformation from a spherical or circular shape, do you take that into consideration?
So the deformation is actually sort of incorporated in these potentials themselves. Sorry, so let me just go here. The potentials themselves incorporate the deformation. So for example, this alpha, if it is 5 by 2, that actually takes into account the elastic deformation energy that is stored in these. So so this is of course an artificial looking model, but really you should be thinking of these as deformable particles where the elastic energy stored gives rise to these effective Hertzian potentials, for example. Yeah.
Okay.
So, but these are for small deformation, not large deformation. So eta large doesn't mean that the particles actually move into each other, but they just represent large changes in the distances between particles. For example, eta here, it's not that the particles are all going through each other. They're just very large polydispersity in their size, but the deformation is included. Yes. Yeah.
Thanks.
Yes, please.
See XXX that you showed.
Yes.
It was independent of Q. I mean,
no. So this is Q. This is QX.
The expressions that you showed.
Oh yeah, absolutely. So this is the. This is sort of a hallmark of these pinch point singularities. I'll let Subhrot explain more.
Slide, yeah.
Yeah. So here, in the Q going to zero limit, they only depend on the angle in Fourier space. This is sort of a consequence of the fact that you have an elasticity theory in this model. Yeah. So that's what we mean by pinch point singularity. That they depend on the angle with which you approach Q equal to 0, but they don't have a Q dependence in that limit. Yes. Yeah.
Okay. Thank you.
Yeah. Thank you.